Welcome back, everyone. So this week we are going to talk about infrared spectroscopy, or IR spectroscopy. So part of chemical work is being able to understand the structure and being able to determine what the structure of whatever you've purified is. And there's a couple ways that we can do this. As you've seen through the lab, we've used nuclear magnetic resonance, or NMR. And this works by exciting the nucleus using radio frequency. And as we've previously seen, this is very good for proton NMR or carbon NMR, and it allows us to kind of figure out the backbone of our molecules and stitch them back together piece by piece. The other thing that we saw this semester was using infrared spectroscopy, which triggers molecular vibrations using infrared light. So we've been able to use this to determine very special functional groups like alcohols, carboxyl groups. And so this is a very useful tool when finding, I guess, these functional groups. There are also a couple other, methods that we can use to determine a structure. One is mass spectrometry, where we kind of bombard the sample with electrons. And what this does is it completely obliterates it, but we can measure each of the pieces. So we will have actual chunks, and with these chunks, we can stitch them together and recreate our molecule. And finally, we also have ultraviolet spectroscopy, or UV spectroscopy. And this works by promoting the electrons to a higher energy level using ultraviolet light instead of infrared light. And this is mostly used to gain information about conjugated pi systems, as well as the presence of any double or triple bonds. So as I said, infrared spectroscopy, it works by using infrared light to irradiate our molecule or our compound. And the IR spectrum of a compound can provide very important information, such as its chemical nature or molecular structure. And what's most common about it is the spectrum is obtained by measuring the absorption of this infrared light. So we're measuring the compound's ability to absorb the infrared light, although we can also analyze the emission or reflection. It's a very widely applied tool for the analysis of organic materials, and it's also very useful for polyatomic inorganic molecules as well as organometallic compounds. So it's very useful in a very kind of wide array of disciplines in chemistry. So to understand IR spectroscopy, we need to understand what electromagnetic radiation is. And so what it is it's a radiant energy having both the wave and both dual properties of both waves and particles. So the particles that we're kind of interested in are the photons, and every photon has a discrete amount of energy known as a quantum. So to measure these electromagnetic radiations, we characterize them by their wavelength and their frequency. And let's see. So here's kind of an example of the wavelength. So wavelength is the distance of a peak from one end to the other, while the frequency is how fast it goes. So let's go back here. Yeah, so the wavelength is the distance from one point on the wave to the same point on the adjacent wave, while frequency is the number of waves that pass per unit of time. And this is usually reported in hertz, so distance over seconds, or 1 over seconds. And so the energy is directly proportional to the frequency, so the speed of the wave, but it's inversely proportional to the wavelength. And so when we measure the wavelength, we always use the unit of distances, such as meters, centimeters, although really centimeters and really nanometers are what we use due to how small the distances are. So here you can kind of see we have the wavelength as well as the energy for each of these, different frequencies or different waves. So at the lowest are the radio waves, which have the biggest wavelengths. And remember, the bigger the wavelength, the smaller the energy. As we progress from radio to microwave, we can see that the wavelength starts to decrease, but the energy begins to increase. So infrared light is right below visible, and what we can see using infrared light are the molecular vibrations. As we kind of go further, when we hit the UV light, that's when we can see electronic transitions. And once we hit X-rays, we begin to see ionization. So just remember that as the wavelength decreases, the energy increases, and at the same time we are having higher frequencies. So gamma rays, X-rays, and vacuum UV rays will have higher frequencies and shorter wavelengths. So here is another kind of example of the actual, of the spectrums. So we have radio, micro, infrared. And then as we increase in frequency, we increase in energy. As we increase in wavelength, we decrease in energy. A good note to remember is that ultraviolet is always stronger than visible, which is stronger than infrared. So when you look at the spectrum, just remember that it's going to go violet and then red. So infrared is closest to red, ultraviolet is closest to violet. So just a couple relationships. So here we have the wavelength times the frequency, and that's supposed to equal the speed of light. The kinetic energy is equal to Planck's constant times the frequency, or we can have it times Planck's constant times the speed of light divided by the wavelength. So as you can see, there is a very direct relationship between waves and the speed of light. So for infrared radiation, the wavelength is usually around 2.5 to 17 micrometers, while the frequency is anywhere from 4,000 to 600 inverse centimeters. So these frequencies match the frequencies of covalent bond stretching and bending vibrations. So infrared spectroscopy can be used to find out about covalent bonds in molecules. So we're able to see what types of bonds are present, as well as gain some kind of structural information. So what exactly does the frequency depend on? So here we have a formula of changes in energy equals Planck's constant times frequency. And we can see that if we rewrite this equation, what we end up getting is Planck's constant over 2 pi times the square root of the spring strength or bond stiffness, because if you think about the bonds, when we irradiate them with infrared light, we're causing vibrations as well as stretching. And so these stretchings cause the bonds to act like a spring. So which is why we have a spring constant for the actual bonds. And then so it is the spring constant divided by the reduced mass. So something to take note is that the frequency is directly proportional to the strength of the bond. So V is proportional to K, so our spring constant, while it is inversely proportional to the reduced mass of the atoms. So V is proportional to 1 over U. So what does this exactly mean? So as we increase the weight of the atoms, we can see that the frequency begins to decrease. So starting with a very light atom such as hydrogen, we have a bond energy of about 100 and a stretching frequency of about 3,000. But as we go from deuterium to carbon, the bond energy eventually goes down to 83, and the stretching frequency goes down to 1,200. On the flip side, the bond energies also play a key role. So the stronger the bond, the higher the frequency. So starting with a single bond, we have a bond energy of about 83 and the stretching frequency of about 1200. But then as we add up to a triple bond, it goes to a bond energy of 200 to a stretching frequency of 2200. So just remember, heavier atoms cause a decrease in frequency, while increase in bond strength increases frequency. And so remember, frequency decreases with an increase in atomic weight. And frequency increases when we increase bond energy. So infrared radiation is a very thermal type of energy, and it induces very strong molecular vibrations in covalent bonds. And so, like I said before, this can kind of be imagined as if two atoms are connected to a spring. And depending on how they absorb the infrared light, they begin to vibrate and stretch. So we have a stretch state and compressed state, and we're able to measure this exact vibrations using IR spectroscopy. So covalent bonds can vibrate in several modes, including stretching, rocking, and scissoring. So it's hard to kind of see it on a static picture like this, but we can kind of imagine when we say stretching, it's the back and forth of the peripheral atoms. So the hydrogens are going up, I guess, diagonally, going further away from oxygen and then coming back. There's also the antisymmetric stretching, where while one goes in, the other goes out, then it comes back in and the other goes out. And then the other is bending, where instead of going closer to the oxygen, they kind of go back and forth this way. So they always have the same distance to the main atom, but they are moving closer relative to each other, or closer and farther away relative to each other. So infrared radiation does not have enough energy to induce electronic transitions. So these are reserved for irradiation with UV light. And if the frequency of the radiation matches the vibrational frequency of the molecule, then the radiation will be absorbed, and this causes a change in the amplitude of the molecular vibration. So if we have a wave, if the wavelength is the distance from side to side, the amplitude is the distance from up to down. So the higher the peak, the higher the amplitude. The lower the peak, the lower the amplitude. Infrared spectra are most commonly presented as a percent light transmitted through a sample as a function of the wavelength or energy of light. Meaning, as we shoot infrared light into our sample, we detect how much light has passed through. So we're detecting what has been transmitted. And comparing what we shot at the beginning versus what we got at the end, we can figure out how much of the light was absorbed by the compound. And then samples that absorb all of the infrared light would usually give a spectrum with a horizontal line near the bottom of the spectrum. So this isn't usually the case, but sometimes there are compounds that do absorb infrared light very well. So here is I guess a little model so you can kind of understand. Here we have a source of infrared light that will shoot towards our chemical sample. And this infrared light can do a couple things. It can be absorbed by our chemical sample, leaving some of the residual infrared light to pass through and hit the detector. Infrared light can also hit the sample and bounce back and hit a different detector. Or it could just go straight on through and not get absorbed at all. So there's a couple ways that the infrared light can interact with our sample, and there's different ways for us to detect it. So here is the infrared spectrum in absorption mode. So we're reading the exact measurement of what has been absorbed. So 0% means nothing has been absorbed, and then at 3,600 inverse centimeters, we see a huge peak, meaning at this wavelength, we are getting absorption of infrared light. Vice versa, we can do the exact opposite. Here we have transmission. So at closer to 100, that means nothing is being absorbed. All the light is hitting the detector, and then suddenly it hits 0%, indicative that no light has passed through. We can also classify the bands depending on how strong or weak they are. So when we look at the transmission version of the graph, we can see that the farther the peak goes, the less that has been transmitted, meaning the more that's been absorbed. So when we see these peaks, we can categorize them as weak, medium, or strong. And this is very important because some functional groups will have stronger peaks than others. So here's what I mean by that. So only polar bonds, so not all covalent bonds display on the IR spectrum, only polar bonds are able to. And because these are referred to as IR active. This means that the bands depend on the magnitude of the dipole moment. So strongly polar bonds, such as carbonyl groups, will produce strong bands. Medium polar bonds and any asymmetric bonds produce medium bands, and very weak polar bonds and symmetric bands provide weak or no bands at all. So what do I mean by this? So when we look at our carbonyl group, we can see there is actually a very clear dipole moment from the oxygen to the carbon, making it very easy to see. When we swap out the group to a nitrile group, and the dipole moment is still existent, but it's weaker. And this causes a slightly weaker signal or a medium signal. When we move to a completely carbon-based or organic-based compound, we see that if there is some kind of asymmetry, like we see with this triple bond here, then we're very faintly able to see it. However, if this triple bond is in the middle of the compound and it's symmetrical, then it's almost indistinguishable and we cannot find it. So bands can be either sharp or I guess narrow, as well as broad. So as we saw here, narrow bands tend to be very sharp, very easy to notice, while broad bands take up huge amounts of space. And what's important to know about broadbands is that broadbands may be hiding other signals underneath. However, there are certain functional groups that will always have a broadband, and they're usually very distinguishable, such as the alcohol groups. Alcohol groups in an IR spectrum are going to be your best friends because they're almost the easiest thing to find. So as I said, what we use IR spectroscopy for is the functional groups. It helps us determine what functional groups are on our compound so we can kind of stitch it together. And this provides a very good molecular fingerprint that we can use to compare different samples. Because if samples are pure, they should have the exact same IR spectrum. And if they are the same, then it can't be argued. So if the IR spectrums are the same, then we can be confident that we've purified a pure sample. What IR infrared spectroscopy does not do is it doesn't give us any proof of a molecular formula or structure. All it does is tell us what fragments we have and specifically what functional groups these fragments are. So it's kind of limited, which is why we always use it in conjunction with NMR or UV-Vis. So first I'm going to talk about one certain region, the fingerprint region. So the fingerprint region is the region anywhere between 1500 to 400 inverse centimeters. And this usually holds the vibrational frequencies of the entire molecule. And the reason it is called the fingerprint region is the signals that you tend to get here are very indicative of the molecule itself. And normally, if you have a very pure sample of whatever molecule you're working with, the fingerprint region is so exact you can usually compare it to the like a known version of whatever you've purified. So here we can kind of see the different stretches. Notice how we have the hydrogen stretches from nitrogen and carbon bonds, as well as carbon-carbon, carbon-nitrogen, carbon-oxygen stretches. So this fingerprint region that we see here is very indicative of the whole molecule itself. Meanwhile here, going from, I guess here is like 1200 to 4000, we can see different bends and stretches that are more akin to the functional groups. And these are usually the ones that we read. So when you analyze an infrared spectrum, it might be difficult to look at anything in the fingerprint region because there's so many signals. There's lots of signals that show up here, and they all kind of overlap each other, so it's really difficult to get a very concise measurement. So for now, when you analyze an infrared spectrum, focus on the group frequency regions. So here's what I'm talking about. So here we have the spectrum for 1-butanol. So from 1500 and up is our group region, and below is the fingerprint region. And so you can see a lot of crazy signals here in the fingerprint region, and because of this, it makes it very difficult to kind of figure out what, I guess, any functional groups, if any, are here. So one that they highlight is for the carbon-oxygen stretch. However, this is incredibly unreliable because we have so many peaks here that kind of make it difficult to figure out. On the flip side, if we look at the group region, we can easily see this alcohol broad peak, which is very indicative of that alcohol. So it at least lets us know that we have an alcohol functional group. So please, when you work with IR spectrums, try to focus above the 1400 range. So again, the typical IR absorption ranges for covalent bonds is anywhere from 600 to 4000. So this is the entire kind of absorption spectrum. And so when we look at this graph, we can see the different regions of spectrums where different bond types can normally absorb. For example, around the 2200 to 2400 region is where we see where we can find if there's a possible presence of nitrile groups or carbon-carbon triple bonds. So let's begin by looking at the IR spectrums of alkanes, because these are probably going to be the most important that we see. So their IR spectrums usually display only the carbon-carbon or the carbon-hydrogen functional bands or bond vibrations. So when we're looking at pure alkane molecules, the most useful ones that you're going to need to find are the CH bands, which appear at the 3000 inverse centimeters range, or 3000 wave number range. So because most organic molecules will have these bands, you'll be able to normally see these bands. One thing I kind of want to note is that for this 3000 range, it's very important that you see whether the peak is above it or below it, because these can be two very different alkanes, and these can be two different types of carbon-hydrogen stretches. And you'll see what I mean as we progress. But as you can see, if it's lower, this can usually be indicative of the saturated carbon-hydrogen stretches. So your sp3 hydrogens. Now, what if we were talking about alkenes with double bonds? So remember how anything below the 3000 is usually indicative of sp3. Well, something above 3000 could be indicative of the double bond or an sp2 hybridized hydrogen. So when you're working with an alkene, try to focus on the carbon-carbon double bond stretching vibrations that can be found either above the 3000 range, as well as the 1600 to about 1700 range. And you can see it's a very sharp peak here. So try to focus on this one and this one. So here you can kind of see that depending on the spectrum, the peaks can be a bit obscured by some of the broader bands. So we can see that, yes, we have that when we look at our carbon-hydrogen stretch, that most of the peak, there we go. So as you can see, most of the peak is definitely below 3000, and we can see this little tiny peak here. This can be really hard to distinguish and really say for certain if you're working with an sp2 hybridized or an sp3 hybridized hydrogen. So just keep that in mind. So now moving on to alkynes. When you're working with an alkyne, the most prominent band that you're looking for is it's going to be a sharp, so very narrow, but a weak band at 2100. And so remember that IR spectroscopy is not very great if the sample isn't very polar or the functional group isn't polar. And remember, triple bonds are not very polar, which is why we see a weak band. But we can use this to our advantage. Just because it's weak doesn't mean that it's a bad thing. However, maybe we might have a very highly symmetrical alkane, and if that's the case, we may not be able to see anything at all. So if we have an alkane that is near the periphery of the molecule, then we can maybe think about seeing it on the IR spectrum. Something else to note is because these hydrogens involve, because these hydrogens on an sp bounded carbon, we should also expect to see a peak above 3300, which is again correspond to these carbon-hydrogen stretch. When we're looking at alkynes in the middle of the carbon chain that do not have the carbon-hydrogen bonds to the sp carbon, we kind of expect to have a lack of a band or a peak. So here are the examples of 1-octyne and 4-octyne, where we have the triple bond closer to the edge of the molecule and the triple bond in the middle. So when we look at the first example where the triple bond is near the edge of the molecule, we're able to see a very clear peak above 3000, which is again indicative of something other than an sp3 hybridized carbon. Because it's so high up, it's very easy for us to say this is probably an sp hybridized carbon. But the most prominent peak is the one here at 2119, which is indicative of that carbon-carbon triple bond stretch. Now what happens if we move this triple bond into the middle, where it is no longer polar? We lose both the peaks, so we won't be able to see them. So just remember to keep that in mind. Depending on where your triple bonds are, this can mess up your reading. Okay, so then what about nitrile groups? So for nitrile groups, we can expect a very prominent band around 2250. So you can see this really sharp peak. Notice that for the carbon-carbon triple bond, it was around 2100. Oops. And for the nitrile, 2200. So these are around the same area. So you can expect to see whenever there's a triple bond, look around this 2200 area. Alcohol, look for the big hump. That's really it. Alcohol is the only one that has this giant broad peak from 3000 to 3700. If you have an alcohol, you should see this peak. It's always going to take up a big chunk of the space, and it's always going to be big and broad. So what about ketones and aldehydes? So remember, carbonyl compounds are the ones that contain the carbon-oxygen double bond. And so because of this, they tend to be very polar. Something to keep in note is remember that aldehydes have a hydrogen attached to the carbon, while ketones have two other, usually carbons, attached to the carbon. So as a result, the carbon in an aldehyde, that is usually, as a result, the carbon in the carbon-oxygen bond bonded to aldehydes is also bounded to another carbon and a hydrogen, whereas the carbon in a ketone is bound to two carbons. So when we know that we have an aldehyde or a ketone, we should probably look around the 1710 to 1720 range, which is usually right in the middle of the spectrum. And because it is polar, we should expect a very sharp, strong peak. And so another thing to remember is aldehydes contain an sp2 hybridized carbon because of that carbon-oxygen double bond. So because it is sp2 hybridized, we should also expect to see a carbon-hydrogen stretch at 2700 to 2800. So let's look at an example of an aldehyde versus a ketone. So again, both the aldehyde and the ketone will have the carbon-oxygen stretch around 1700 to 1800. Meanwhile, the aldehyde will have some extra peaks for the carbon-oxygen, or the aldehyde, the sp2 hybridized hydrogen, you can kind of see here, while the ketone does not. So just remember, if you're working with an aldehyde, you should see something definitely below 3000 for this carbon-hydrogen sp2 band. So just remember that when you have a carboxylic acid, you should see both the carbonyl group as well as the alcohol group. And so the next spectrum that we want to look at is that of the nitrogen-hydrogen bond. So this bond is usually positioned at the left of the spectrum, really high up, around 3200 to 3600. And you can see that it's a very, very weak band. So if you know that you have a nitrogen that I guess that is only bound to a hydrogen, you can kind of expect a very weak band really high up in the spectrum. So primary amines have two nitrogen-hydrogen bonds. So they typically show two spikes. Secondary amines will only have one hydrogen bond, which will give them one spike. And tertiary amines, which have no hydrogens, will not show up at all. So what about amides? So amides are functional groups that contain a carbon-oxygen double bond, where the carbon is also bound to an amine. So the amide functional group combines the features of the amines, the amines, and the ketones. And because it has both the nitrogen and the carbon-oxygen double bond, we should expect to see both. So here we have the stretch for the carbon-oxygen double bond, and you can see it kind of moved a bit down to 1630 to 1660. So I say these numbers, but remember that these peaks can shift a little bit left and right. So it's really hard to say exactly look at the 1700 range because we can see something go below that. Meanwhile, here we have our NH stretch. So we can see that for our molecule, it is a primary amine. So we have two hydrogens. So we should see two peaks. So that's pretty much all of the major functional groups of the IR spectrum that you'll need to know. Again, when you analyze an IR spectrum, the peaks can shift a little bit. So if you know something should be there, but the peak is a little bit lower or a little bit higher than you would normally think it could be, it could just be something with the molecule, and it could actually be the right peak. And then second, when you're analyzing these spectrums, just please try to stay above the 1400 range. Looking down below is going to be fairly difficult just because of how many peaks that show up that can kind of mess up the signal.